Okay. Just need some coffee. So welcome back. So what are we going to do now? I'm going to motivate, of course, why it is that we are looking into syntax. This is actually something that we have to deal with in big data that we try to get rid of in relational database systems, of course. But somehow it's a necessary evil because of the way we need, to store data sets, to share data sets. When you share them, they need to be in some formats, right? So you might remember the data shapes that I told you about at the very beginning of the lecture. Unstructured data, cubes, trees, graphs, and tables. You really need to know that by heart. This is the very beginning when you deal with data. And of course, we are focusing right now on trees, which I will give you the intuition are denormalized data, the trees. Tables, that's what we did with the PostgreSQL, the SQL brush up. Now we're going to tables. The graphs and the cubes, don't worry, we'll see them at the end of the semester, but a lot of what we'll do in the coming weeks is tables and trees. So remember this big technology stack that we are trying to build. It's technically the same one as we had in the 70s with relational database systems, but now we are trying to rebuild this on top of clusters of thousands of machines. So now it's nice because we have this checkpoint right there that we have the storage, right? So here we basically validated this, right? And now we are going to look a tiny little bit into encodings and then into syntax. And then in the coming weeks, we'll just work our way up all of the other levels of the stack. So just so that you are aware, I still want to give you a sneak peek of what's to come. So at the syntactic level, of course, there's text, right? But you might know of CSV, right? Comma-separated values. Every business person knows about CSV, right? It's really, you find it on any website, you can download the data as CSV. Technically, it's tables. XML and JSON, that's for trees, for denormalized data sets. I should have written YAML also, you might know YAML. RDF XML, that's actually for graphs, Turtle as well. It's for graph data, and XBRL is for cubes, right? So you see there's a syntax for pretty much any one of the shapes. All 5 shapes actually are represented here, right? And this is how you actually serialize that, all of that to text that you can then encode and store on the data lakes, S3, HDFS, and so on. So now, just for the sake of having talked about it, a few words on the encoding. The encoding is just the missing link between a system like HDFS or S3, it stores bits, right? It doesn't store text, it stores bits. And with syntax, we want to store text, right? So we need a way to map the text to the bits. That's pretty much the idea of what an encoding is about. Now, there's plenty of encodings out there. There's the first ones that are quite old right now, like ASCII. That was an encoding specific to the English language, where you were mapping just 128 characters or special characters to 7-bit sequences, right? Then you started having extension like ISO-Latin 1, but actually there's many of them that extend this with special characters for German, for French. But in fact, you got them also for many other languages, right? For I don't know, Chinese, Korean, Hindi, Russian, Arabic, Japanese, and so on. So all of these languages need special characters. So then at some point, there was plenty of character sets that were invented for this, until finally, one day, all of that was unified as a single standard called Unicode, right? And Unicode is a catalog of characters. It's pretty popular now with emojis, because now you see every couple of years there's an update to Unicode with new emojis. That's because we're kind of done with the alphabets. UTF-8 is one of the ways that you can store Unicode, right? It's one of the ways that is kind of elastic. For the ASCII characters, they will be on 8 bits, but then it can extend to 16, 24 or 32 bits, depending. I will show you. UTF-16 is yet another encoding related to Unicode. Do not confuse Unicode with UTF, whatever. Unicode is a catalog, it's a character set. It just maps the characters to numbers. An encoding is going to use the catalog to map these to actual bits. Okay, so this is ASCII. That's for historical purposes. If you write new software, do not even think of using ASCII. Now, UTF-8, Unicode, maybe UTF-16, I don't know, but UTF-8 is kind of the standard now. So whenever you write a piece of software, if you create a new startup, make yourself international from the very beginning, because then if you expand to other countries, it will just work, right? Okay, so UTF-8 nowadays is the way to go. And you can see with P, that's the English alphabet. So this only takes less than, I should have written less or equal to 7 bits to be more precise. That maps to UTF-8 in this way, where you have just this 0 that says this is the only packet, and that's it. That's the encoding of P. Pi now is higher. It has at most 11 bits, so you need 2 packets, right? And the 110 tells you this is the first of 2 packets, and the 10 is a continuation flag that tells you this is another packet coming after this one, right? And then the euro sign that came even later has less than 16, less or equal to 16 bits. It starts with 1110 that says it's the first of 3 packets. Then you continue. Everything that is marked in bold here is basically the bits of the character, and the ones marked not in bold here correspond to just what pastes it all together, right? That tells you when a packet, a group starts and when it stops. Okay? Does it make sense? Right? This is Unicode. That gives you the superpower of being able to put pretty much any character that exists in the world into bits just without thinking about it, right? So that's the standard now. Okay, so this is the encoding. So now you know how text can be mapped to bits, and you also see that it's not trivial at all. You've already pretty much experienced, I'm pretty sure, who has already tried to open a file in a text editor or import a CSV file into a spreadsheet software, and then you will see all kinds of weird characters that appear, right? Almost everybody, right? And this is because you're not using the right encoding. That's pretty much the story. Okay. Now about data denormalization. I wrote data denormalization 101. You might remember that I told you in the introduction about normal forms, right? There is the first normal form, the second normal form, the third normal form, the 3.5 normal form, the fourth normal form, the fifth and the sixth normal form. And the good news I have for you is that this is because we're throwing them away, which is actually good, especially for those of you who might not have seen them before. So I'm just going to give you the intuition. This is CSV, what you see on top. This is a comma-separated value file. You basically have the headers typically on the first line, comma-separated, and then you have the values on the other lines with hopefully the same number of commas on every line. And technically, when you open that file, you can open it in spreadsheet software, actually, you will see a table. Who, just to get an impression, if you look at just this, who sees the table here? Okay, great. My goal is that when I show you the other syntaxes and I ask you who sees a tree here, I would like also at the end of the course, all hands to be raised. I want you to see trees. I want you to see graphs, to see cubes in the syntax, right? The syntax is just text, but you parse it and see it in a certain shape. Okay, so this is the actual table that it's about. Just so you know, it sounds simple right there, right? At first sight, it's actually very complex. There's technically a standard called RFC 4180. The problem is that as for every standard, many people don't respect them. So in fact, every time you're going to see CSV, you might see all kinds of weird things happening. But more or less, the way that it usually works is that you can have quotes in order to escape the commas, right? For example, this comma right here, you don't want to treat as a comma separation. So you add quotes, but then you just shift the problem because now how do you escape quotes? And you escape them by actually, so this is the first quote, and then this is a double quote that is the escape of an actual quote, right? So here, and that's closing. So in fact, this here is the syntax for this. So this quote here is doubled, and this one is doubled in this syntax, right? Again, this is opening the string. This is an escape for the quote that is here. Incompleteness, this is an escape for the quote that is here. Theorem, and this is closing the string. For whom does that make sense? Okay, now you have variations. Some people don't like commas, so they use semicolons, tabulations, and so on. So there's plenty of ways you can do this. The end of the lines could be just a line feed, a carriage return plus a line feed, which can be also OS dependent. There are other ways than the quotes to escape. So you see, it's really more complex than it seems. And I think a lot of people doing machine learning also know that, because you need to import this thing often in machine learning software. And also here, it all starts with configuring the flags in how to open it properly, right? Okay, so this is CSV. Now, we saw that CSV is for tables. And when you have a relational database management systems that has tables, we learned that there are normal forms that give us a best practice of how to store data. And the idea of normal forms is that you should spread your data over multiple tables where every table has some meaning. A table of people, a table of products, a table of courses, a table of universities, and so on. And if you have done your job well, then in a case that you're updating your data a lot, you have a lot of people placing orders on your website and so on, things will go smoothly if you have data in normal form, right? Well, here, we are not interested in actually modifying the data. We are doing data analytics, right? We are interested in reading the data. So we are going to assume that we downloaded some data set from the internet. We don't want to update it or modify it with 1,000 requests per second. We just freeze it and read it as it is. Well, when we do this, this is no longer needed. This is no longer needed because we don't need the solutions to the problem solving, because we don't have the problem in the first place, right? So we don't have any anomalies, so we can drop all of these normal forms. And again, the idea is really this spectrum between write-intensive and read-intensive. Write-intensive is the database behind your business that just is operating and hopefully successful with millions of customers that keep updating your database via the website. Highly normalized, you want to avoid the anomalies. But if you want to just analyze data, it's read intensive, highly denormalized. You really want to put it back into some single big table that will be denormalized, might not even be a table at the end, and you want to avoid the joins. So denormalizing is kind of like joining back to a single table. Just so you know, because I will come back on that, there is a name, an acronym for that, that's called OLTP, Online Transaction Processing, and this is called OLAP, Online Analytical Processing, right? It might be that you heard about OLAP in the context of data cubes, but it's really more general than that. OLAP is really about read intensive, and this is write intensive. This is also why we love data lakes. When you read intensive, then a data lake actually can make sense. All right, now let me give you an intuition to make sure that we agree. This is normalized. This is in Boyce code normal form. Technically, it means that all of the functional dependencies that are not trivial, they have a super key on the left. And in English, that basically means that we have multiple tables, and every table does one thing. We have a table of products, table of sales, table of customers. And when you query the table, at runtime, you have to do joins, right? You can join the product here, that is a product ID. It's a foreign key pointing to that product. And here you can join some customer ID. That's a foreign key pointing to your customer. Of course, here it's ridiculous because there's only one column, but of course there's going to be name, first name, address, city, phone number, and so on and so on, right? But basically, this is in normal form. And if you denormalize it, you put it back into just one table where you see there are duplicates that start appearing, but this is fine. Now, the idea is that a table is a collection of tuples, right? Every tuple is a record. Record, tuple, row, this is all equivalent. So a table is a collection of tuples. And one tuple or record is actually mathematically a map that associates attributes to values. For example, in this first tuple, the first row of the table, we associate the attribute product with phone, price with 800, customer with John, quantity with 1. So that gives us a map, right? This is a mathematical, it's called the partial function, technically in mathematics. Partial because we don't map all the strings, just these 4 strings to a value. Okay, now I'm going to take one small step, but it's a giant step for big data. This is the JSON syntax that we are going to talk about, right? It's just equivalent. This is just a more computer science-y version of the mathematical map. And we have these curly braces and commas and columns, and you will basically get used to it. But I'm sure a lot of you already saw, who already saw JSON? Who never saw JSON? Some of you. It's okay. I'm here to teach you that, right? So this is JSON. And I want you at the end to see the tree. That when I showed you JSON or XML, I want you to see trees in there, but we'll spend a couple of weeks on that. All right, now if you have just for one record, we can have this JSON object. We can have one JSON object for every record. And technically, this is the syntax that corresponds to my table, but it's no longer CSV, it's JSON. So now you might tell me, okay, why don't you use CSV? It's so much better for a table. Yes, but CSV cannot be denormalized for some reasons that I will show you. But with JSON, we'll be able to denormalize and still store it in JSON. So that's the key. So remember this big picture that in the beautiful world of relational database management systems, we have relational integrity, atomic integrity, and domain integrity. That's what gives us an actual relational table. And here we throw everything away, and we are in the NoSQL world. Not only SQL, it's not that we're throwing SQL away, it's just that we're extending or looking at new things that we can do beyond SQL, right? So this is where we are. And it's not just that we are joining all of these tables into a single table, is that even the first normal form, remember, the first normal form is when we don't allow a table in a table in a table. Well, if we throw that away, then we do allow table in a table in a table, right? So we throw all of that away, and this we allow now. We are perfectly fine with this, right? In your bachelor's of computer science, we told you this is so bad to do this, but I'm telling you this is good. Just put it in a data lake. This is denormalizing your data. Okay, so I'm allowing you to do that. And we can do it in JSON here. And you can see that the way that I'm nesting my table in there is with an array here with objects in there. And this is the intuition I want to give you, that here we can denormalize using the JSON syntax. In CSV, you cannot do it. You could hack your way into it in CSV with some convention, but it's not meant for that. Okay. And even worse, here it's not just that it's a table in a table. We might even have this kind of things that some values are completely missing, right? So in that case, that's perfectly fine, because in JSON, all I do is remove the pair here, and that's totally fine, right? It's perfectly fine JSON as well. In CSV, well, maybe you could just put a comma right after the former comma and it's empty, right? But technically, it's not the same thing, because in CSV, it's just a null if you don't have anything. Here, it's really absent. So what am I actually doing if I have this? This is a very important slide. It pretty much summarizes what we get into when we denormalize the data. We basically have these flat homogeneous tables, which is if you have all of three constraints, the relational database systems. And if you denormalize data, these things are going to happen. You're going to have extra values. In one of the tuples, you're going to have a new attribute that you didn't see elsewhere that is associated to a value. You're going to have missing value. An attribute is just missing in one of the records. You're going to have invalid values. Maybe this attribute is associated with an integer everywhere, except here where it's associated with an array of integers. And this is fine, it's denormalized. So this breaks domain integrity. You might have nested values in there, nested structures. In that case, it's tables, but you can actually pretty much nest anything you want, even more messy than that. And this is just another table. Here, it's both that you nest tables, and it's not even the same in every row, right? Here, you have three tables, and here you don't. Here, you have a table, and here you don't. So that's what we call messy data, right, as the code name for that. And in big data, we have to deal with that kind of data. Why is that? Well, an example of why is that some of the data sets, I'm thinking of GitHub, the GitHub archive that we've used in past exams. This data set has been accumulated over many, many, many years. And what happens when you store data across many years is that you might change the format of the data. 1 year, you make a decision, now we're going to change the way we format that data. But typically, when you do that, this is not retroactive. The past data stays the way it is, and you just start outputting in a different format. This is how you end up with that sort of things, because you change the schema 1 year, and then you end up with that kind of data. And if you want to fit it or force fit it into this, you can. With a hammer, you can force your way into this. This is a lot of work, but having technologies that can handle this make it easier. You still want, ideally, to clean up all of this data in order to transform it into something like this, for example, to feed it into machine learning pipelines, but we need tools for that. And we need better tools that using grep and parsing strings, right? We really need tools that understand this idea of collections of trees, right? To facilitate cleaning up the data. So we are moving on from the good old world of the 1970s with relational data, homogeneous collections of flat items, and we are moving over to heterogeneous collections of arborescent items. Arborescent is just a beautiful name for tree-like, right? An arborescent structure is just a tree structure, a hierarchy, right? So I put here some of the drawings because sometimes you manage to draw something equivalent, and this is the JSON syntax. In some cases, the data is so messy that you cannot even draw anything, right? So that actually happens. But in that case, I could. For whom is that clear, right? We move to heterogeneous and nested data, arborescent data. Now it's a whole spectrum. If you don't denormalize the data, you are structured. If you have something fully unstructured, that's text, images, videos, audio, and so on, you're here. And what we have here is in the middle. It is not quite structured, it is not quite unstructured, it is semi-structured. And semi-structured is the code name for trees, right? Everything around JSON and XML. Now, these are standards, and XML is something that is standardized on the side of the W3C. So the W3C is this international consortium that defines, for example, HTTP, HTML, but also XML and others. Now they're working on password and authentication without passwords. And ECMA is another standardization body, and this is the one that standardizes JSON. Actually, JSON used to be an RFC, well, it still is, but then there was an ECMA standard made about it. And ECMA is also the ones that standardize JavaScript, also known as ECMAScript in the standard. All right, so it's all standardized. It's so important because if you have a standard, it means that you can use a search engine. I was about to say a name, but I'm just going to remain general. You can basically search for libraries that can parse XML or JSON. You will find thousands of them. So if you're looking for a specific format of like configuration file or anything, you should just go ahead and use that. XML, JSON, YAML, something standardized. If you don't, then it's up to you to write your own parser. And why would you waste your time doing that if you can just use a standard, right? So this is the idea. And XML is a bit stricter than JSON. So XML is really very strict about the rules. JSON, we will see, is a bit more lenient. It can still accept some input even if it breaks some rules, but this is the idea. So this is why it's so important to have standards, because you can just download free and open source tools. They are all over the place and in any language, in Java, in Python, you can find them in almost every language. All right. So now I'm moving on to actual syntax. Why do we need syntax? It's like CSV for tables. Well, for a relational database management system, maybe I don't need CSV, right? I can just put my data in there using SQL and that's it. But the problem is that if I want to analyze data, I might want to share it with other people, right? I might want people to download the data set. So if you want to download the data set, you need some syntax for it, right? So this is why you find CSV available on some websites, and XML and JSON are also natural candidates for data sets. There's also YAML and plenty of other formats. Now, this is one thing that you can download and share with other people, download over the network. The other thing is that you can store it in a data lake, in S3, in HDFS, on your local hard drive, and then you can start reading your data. First, you can use Python and Pandas. Then you can also move on to some large-scale system that is more data independent. But basically, you also need to store the data in some way. What I want to add also is a different motivation for the syntax, because it might not have escaped you that this is inefficient. XML and JSON, right? That's not the most efficient way to store data. You see, there's plenty of redundancy here. I'm repeating the labels and so on. And it's true that actually, in many cases, you can find more efficient formats, binary formats. I'm thinking of Parquet, Avro, and so on. So there are other formats, but there is a problem with that. And the problem, it's actually a general problem that there are researchers working full-time about. You share a data set like that in Parquet. Somebody downloads it, it works. Maybe in 1 year, it works. In 5 years, it works. In 10 years, is Spark still there? What if it's not? How do you open it? The data is gone, right? You cannot read it anymore. Having a text format, something that you can open in a text editor, even imagine that we lose all of the XML parsers and all of the JSON parsers in 10 years. You can still open it because that's a text file. You can open it in an editor, a human can understand it, so it's not lost. And in fact, so there are data now, if you do some research, there are journals that allow you to share your data sets, share your data. For example, Data in Brief is one of these. And the ETH research collection allows you to store the data there. And some of the journals acknowledge ETH as a valid repository for the data. And if you look at the requirements that the ETH library has about the data, they will not accept fancy formats. They will not accept anything except super simple things like text, things that you can open in the future, even if the technologies have evolved. So this is really a long-term thing. This is the importance of sharing your data sets as text. But we will see that it doesn't mean that when you query it, it might be a good idea to convert it to something more efficient for the duration of your query. Okay, so this is why syntax. Now, I want to relate and connect that to theoretical computer science. I'm sure you had theoretical computer science during your bachelor's, and you probably heard about languages, right? Who heard of languages in that context, right? And you probably heard about, I don't know, of course, when I want to say it, it's gone, the regular expressions, right? Or you heard of context-free grammars and so on and so on. So there's all kinds of classes of languages. But what is really a language? It's just a set of strings. And either some string belongs to that language or it doesn't. So it's really a question. Is it in the language or is it not in the language? And then you build software, can be, for example, for regular expressions, some sort of deterministic automaton, right? And you can build technologies that tell you yes or no, it belongs to that language. Well, XML and JSON are languages, exactly in this way. There is a set of all documents that are XML, and there is a set of all documents that are JSON. And we have a fancy name for saying that a text document belongs to the XML language or the JSON language, and that word is well-formed. We have a question over there? Almost, yeah.
If you can nest XML inside XML, is that set countable?
Oh, that's a fancy question. I think it has to be countable because these are really strings, right? So you're really let me think. Yeah, that's because I'm in a live lecture. I think it is countable because you are considering finite strings. It would be uncountable if you would also consider infinite strings, right? If you take real numbers, for example, infinite streams of digits are uncountable, but here I think it's countable.
In particular, infinite nesting.
You cannot have infinite nesting. Yeah. It has to be finite,
yeah.
Right? Again, this is something we do with computers to query data. So the constraint we have is that it fits on a machine, and that is finite, right? Mm. Okay. So now I'm giving you a preview because we only have a few minutes left. This is what XML looks like. For who knows HTML, okay, that might remind you of HTML, and they are actually cousins. They are both descendants of something called SGML that was in the publishing industry long ago. So this is XML. You recognize these angle brackets, right? This is JSON. You recognize the curly braces and the arrays. So we look at these two. I'll also show you YAML, so there's others, but this is the idea. So next week, we'll take, tomorrow, we'll take some time to discover the JSON syntax. I'm starting with it because it's simple. And then we'll look at the XML syntax, and then you know everything about it. And again, I want you to see trees. This is a tree, this is a tree. Who sees a tree here? Some of you. At the end, I want everybody to see a tree in a couple of weeks. So now, just checking that you followed what I've been telling you before I let you go. Just a moment, if the network works. Okay, so since the network is still not working, thank you very much for coming today. I'll see you tomorrow at 9 a.m. where we'll dive into JSON of XML. Thank you very much. Have a nice evening.